Hello everyone, my name is Jain Sitaram Sure. So I have an ISA activity of heat and mass transfer, and that is design a composite wall for cold storage. So let's see. So this is the problem statement you are seeing. So problem statement is given as I am working as a mechanical engineer, design engineer for cold storage facility. The facility must be maintained internal temperature of -20 degrees Celsius, while external ambient temperature is 35 degrees Celsius is given. And objective is minimize the refrigeration load by optimal design composite insulated wall subjected to practical and economic constraints. The total wall thickness is fixed at 0.20 meter. So let's see first step. First number is 59. So I have taken a value of AB is 59. So first I have calculated insulation of first insulation thickness. In that 6 is constant and 59 mod 3, that is 59 divided by 3, that comes 19 and again 19 into 3, that comes 2. So I have taken 2 here. So 6 minus 2, that is equals to 4 centimeter and 0.004 is meter. So as I derive second insulation thickness, we have given that since the total middle layer thickness must be 10 centimeter, then 10 minus 4, that is comes in first insulation thickness, and 10 minus 4 6 centimeter. We have converted this into meter. And next step is outside convection. So 12 is a constant, so 12 plus again 59 mod 2. So mod 2 value, 59 mod 2 value is 1. So 12 plus 1, that is 13 watt per meter square Kelvin. Calculated wall surface area, that is 5 plus 0.06 into 59. 5 is constant, so value comes 7.95 meter square. To minimize the refrigeration load, these materials are suitable. First is a vacuum insulation panel VIP. That K1 is given in the table itself, and second material is the aerosol blanket. This value of K is also given in the table itself. So we will move further.
Start.
So next step is thermal design analysis. So thermal resistance network, the heat must pass through all 5 resistance in series. Like first is inside convection, next I have taken FRP layer, then VIP layer and aerosol layer, and last is the concrete layer and outside layer. So we will move further. So I have calculated resistance of each layer here. So first is resistance of convection inner layer. So as that wise I have calculated for all layers, you can see, and then I have calculated total resistance. I have added all these resistance together, and the value comes is 2.07234. So next is load calculation. So I have calculated load calculation here. Like 35 degrees Celsius is given, and we have to maintain -20 degrees Celsius. So we have calculated this. So it comes around 55 Kelvin. So total refrigeration load. So how to calculate this? Delta T divided by R total. So it comes around 26.54 watt. And next is heat gain per unit area. So Q divided by A, if we calculate this, so it comes around 3.34 watt per meter square. So next,
Start.
sensitivity analysis. So how to calculate it? So if we do R divided by RC, so into 100, so it comes around for VIP layer 60.7%, and for aerosol layer that is 36.4%. So that also I have do for other layers combined. It's around 2.9%. This is roughness check. So if moisture absorption increases, that is K insulation by 15%. So I have calculated new total resistance or resistance for each layer here. So for VIP layer, resistance is 1.09, that is new resistance. I have calculated again by dividing 1.15. So each layer total new resistance is comes here. So material and volume selection. So total middle layer thickness is given 10 centimeter, that is 0.10 meter, and first insulation thickness is 4 centimeter, that is 0.01 meter. So next second insulation, that is given 6 centimeter, that is in meter 0.06 meter. So surface area I have calculated 7.95 meter square. So I have done cost analysis here. The cost analysis is calculated based on the volume of each material required for the specific wall surface area of 7.95 meter square. So material is it is listed. First is vacuum insulation panel 0.04, and volume is given of that layer 0.38 meter cube, and cost for unit cost is given, that is 1500, and so for what area we require that material, that cost is I have listed here, that is 477 rupees. And next is aerogel, likewise it is also same for other with and without insulation comparison. To justify engineering design, compare heat gain per unit area. So let's compare. Heat transfer rate without insulation, that is 113.5 watt per meter square, and heat transfer rate without design with insulated, that is 3.34 watt per meter square. So we can clearly see the difference here. So total reduction in heat leakage is 97.06%. So last is justification of material selection. So VIP and aerosol, why I selected this VIP and aerosol blanket. So efficiency or what you can say, the thermal resistance is more for these materials. So efficiency achieved, that is 97.0% reduction in heat current compared to the uninsulated baseline. So space, VIP and aerosol provide the highest thermal resistance possible within the fixed 10 centimeter thickness that is given. So I have just mentioned this. So robustness, the FRP layer serves as the vital moisture barrier to protect this loss identified in this sensitivity analysis. As mentioned in the problem, if moisture is increased by 15%. So to prevent that, I have taken this. Thank you.